Okay, so thanks for joining this very interesting workshop today. I'm just now gonna give you a very brief introduction about all our, let's say, POC or proof of concept of this amazing emerging technology. So as all my colleagues so far just shown you, basically we had a huge number of theoretical contents. Basically, everything was, let's say, our approach was starting from the theory and then getting into some practical and let's say hardware implementation issues. So basically what I'm going to show now, it's what from the project perspective and from our RISE-6G project perspective, what we plan to have as, let's say, POC, as proof of concept, that then what we can really give as input to our two amazing field trials, as my colleagues will show you in the next presentation. So basically, this was part of the work package number 7. Basically, the work package number 7 was just designed and devised just to provide all the insights for building POCs, proof of concept, of our amazing technology. And then this was used as input for 2 real field trials in 2 realistic scenarios. So basically the idea, or let's say main objective for this work package of all these activities under this work package was to devise, let's say, the overall risk-based solution based on the architecture provided by the WP2, the work package number 2, based on all, let's say, the models developed in the work package number 3, and then based using as input all the outcome and the results, the theoretical results coming from the 3 technical work packages, which are work package number 4, 5, and 6, to put them together and to assemble using all the available RIS components, the final, let's say, POC, the final testbed that then can be used into realistic scenarios, into realistic environments. This is an emerging technology, so even the available, let's say, components and equipment is quite limited. When we started almost 3 years ago, nothing was there. So we really started building on top of what we had, real hardware implementation, design of real devices that could be used as reflector, as smart surfaces. And we came up with very interesting POCs, and then also we tried to integrate all of them together to really showcase that our technology and our ideas, our hypotheses were really confirmed. So basically this was the objective of this work package and all these activities. Basically the final object, let's say, will be just to validate the innovations introduced by all the work packages and demonstrate the feasibility of our proposal. Because this means that, after these 3 years of project, we can really say that the RIS is something that can be used, can be implemented, can be installed, it can be used, exploited within real scenarios, within existing network infrastructures. So what we covered as 2 main areas are the extreme coverage enhancement in crowded environments. So we try to rely on the capabilities of our technology to expand the coverage. So to improve the signal coverage for an existing networking infrastructure. On the other hand, we also wanted to target localization. We wanted to target the sensing part of our technology. Basically, what we did was just to leverage on these smart surfaces to, let's say, have advanced localization tools, solutions in indoor scenarios where, for instance, the network infrastructure was already there and we could just deliver an additional service, which one was this sensing or localization. And this was done in a smart factory environment. So basically here you can see very, let's say, just a sketch of this timeline where we have in the first 2 years and a half, the validation of all the RIS components we could really get from all the partners involved in this amazing consortium, plus how we could develop and integrate all those RIS components to create existing POCs. And then I would say in the second half, in the second part of this of the project lifetime, we could have the deployment and the validation of all our RIS components, hardware POCs, into two different specific scenarios, targeting, of course, two use cases. The first one was for, let's say, the communication capabilities, so how to improve it, while keeping the EMF exposure very limited. On the other hand, as I said, we targeted this indoor localization improvement, still using our RIS devices. So basically, what we did after building those POCs was to target different frequency bands, because we wanted really to validate that the RIS proposal, the RIS agreement, could be used within 4 different bands. We had devices, POCs, and demonstrations at sub-6 GHz. Basically, we could target unlicensed band around 5.3 GHz, and also licensed band using 3.7 GHz. We had also equipment working RIS operating within the TA band, so millimeter wave, basically around 27, 28 GHz, which is usually the licensed band for the major European operators. Then we had some demonstrators also at 70, 80 GHz and at 130 GHz, so both targeting D band and V band. So using all of those 4 different bands, we could really try to target again the enhancement of communication capabilities, so just from the signal coverage perspective, and sensing, accurate localization, just using a couple of RIS. And this, was more or less the follow-up of all the theoretical results coming from work package 4 for, let's say, the enhancement coverage and signal coverage, plus the EMF reduction in WP6 in work package 6. And for the sensing part and the localization in indoor, we could reuse all the interesting results coming from WP5, so the work package 5. Everything again was used as input for the final 2 field trials demonstrations. And here you can see briefly what we had. Basically, for the localization, as I said, we could use both SDR equipment, but also commercial devices. For the communication, we could use a real base station. We could just enhance the existing network infrastructure using 5G base station. So basically, as you can see in the next presentation, we could use base stations provided by Ericsson, by Nokia, and let's say deployed in real scenarios, and then operated by Orange in France and by TIM in Italy. So both, let's say, scenarios have just been using existing network and commercial network infrastructure, and then we could really reuse our RIS prototypes, hardware, and so on, to, let's say, complement the existing network infrastructure. So our RIS was able to interact with the existing infrastructure using such commercial devices from, let's say, base station perspective, but also from the UE perspective. And as I said, you will see in the next slide, the first one on the coverage enhancement. The idea was just to have this kind of extreme coverage enhancement at RAN station. So we had a demonstration within a hybrid scenario, the one in a train station, where we could really see the effect of the RIS using the existing network infrastructure composed by 2 existing 5G base stations. Such base stations were like operating at 27 GHz within the Orange license band, and we could really improve such signal coverage in specific areas. On the other hand, we had this accurate indoor localization for AGV for robots moving around within this CRF or Fiat premises in Turin in Italy, within an indoor scenario where an existing 5G base station was already there, and we could just deliver an additional service, which was in this case the localization service, for this AGV moving within a 5x5 meters area. And this was just the last, let's say, activities, preliminary activities before getting into the real, before putting our hands within a real environment, like for the extreme coverage enhancement. Basically, we just had this kind of heat map, as you can see here, for a real environment. Again, this was a train station environment. Basically, this on the left side hand, you can see without the RIS installation, and on the right hand side, you can see after installing 4 different RIS. In that case, as you can let's say clearly see from this picture, we could really improve the situation. We could really, let's say, improve the coverage of the signal coming from those 2 5G base stations installed here and here, where you see these dark red areas. So basically, this was just done again using MATLAB or ray tracing. But then what we did was just to start from this point, start from this hypothesis that was just confirmed by our simulations, and then move to a real implementation, to a real installation of RIS within the real scenario, which means within the train station environment. And this you will see in the next presentation after this. So this is just, let's say, to close this first part on the POCs and field trials. You have already 2 deliverable published in public, the 7.1, 7.2, where you can find all the details about RIS, available RIS components and integration. And now soon, within the next weeks, we are gonna release the last deliverable from WP7, which is the 7.3, that will be focused only on the 2 real field trials. So thanks a lot for your attention, and I will just leave the floor now to the next speaker.
Thanks a lot, Vincenzo. Thanks a lot for the excellent presentation. So I would like to ask to Shokai, I don't know how to pronounce exactly, sorry about, to get the floor for the presentation.
Yeah. Good morning.
Good morning.
Okay.
So please share the screen. Yes. Okay, just try to change the slides to see if it works. Yeah, perfect. Okay, the floor is yours. Thanks a lot.
All right, good. First of all, thank you. Thank you for everybody who's attending, and thank you for the guys who already presented their excellent work before me. My name is Ahmed. I'm from Greener Wave, and I'm here to present today our field trial of the RIS at millimeter wave that we conducted in the train station in Rennes. The field trial was conducted by a team on the ground and supporting individuals from Greener Wave, Orange, and SNCF. The field trial, as I mentioned, was conducted at the main train station of Rennes, France, on the 2nd floor, which is the travelers' access floor for the trains. So usually we have fair amount of human traffic there. It was conducted over 3 days on different crowd conditions. In this trial, we use a bunch of equipments. Mainly, we had access to a 5G millimeter wave AAU provided by Nokia. The equipment is provided by Nokia, installed by managed by Orange. We used a millimeter wave RIS provided by Greener Wave, and for measurement testing, we used also a 5G millimeter wave compatible mobile phone, in addition to a bunch of supporting equipment like spectrum analyzers and computers and software tools. For those who do not know Greener Wave has been working on the configurable intelligent surfaces for the past years, leading the way and providing premieres and publishing theoretical work, providing practical implementation, and conducting trials and measurement campaigns on their products and exploiting this technology in various different fields. The particular device that we used in this trial was, as shown in this slide here. It is made up of a front panel made up of small cells, dual polarity binary controlled cells, a back panel. Let me just hold my pointer. A back panel responsible of routing the control, and a control unit with the housing. Those are some of the specs of the device that we used. As I mentioned, it's the dual polarization with a beam width, achieve a beam width of about 3 degrees. We have a scan range of about minus to plus 60 degrees, and can handle up to like 50 watts of power. But the main feature of the device was it is the power consumption is extremely low. The whole trial was conducted using just batteries, so the RISE itself was powered by batteries during the whole trial. Our objective was to first validate the operation of the RISE in a realistic environment. So we were hoping to illuminate the RISE surface by real infrastructure, 5G infrastructure, and manage to reflect this the beams that are illuminating the RISE into a shadowed zone where those beams are not arriving in a line of sight manner. So the use case that we had here is, as I mentioned, to cover a poorly covered area with 5G millimeter wave using our RISE by redirecting a narrow beam with high gain from the 5G millimeter wave infrastructure into the intended zone. We selected a couple of areas at the train station that are shadowed from the access point. The first zone is, as you can see here, it is a help desk or a kind of desk that's used by passengers, and it is located behind the vending machines or the ticket distributing units, and therefore it is shadowed from the access point. We intended to redirect beam number 20 to this zone, and I will talk about the beams in a second. This zone is around 22 meters away from the access point. Test number 2 was conducted in a similar manner. We are covering an area here that is shadowed from the access point. It is a store in the second floor of the train station used by passengers. We were hoping to redirect beam number 13 in this case to the, let's say, the front of the store and maybe inside the store as well. And this location was 32 meters away from the access point. This is the setup of location number 1. As you can see here in the picture, we have the access point located in horizontal beam near the ceiling of the train station. Our RISE here on the left, and the area that we intend to cover here on the right. We have around 20 meters of distance and like around 5 meters between the RISE and the desk that we are hoping to cover with our beam. In our case here, the RISE was eliminated by beam number 20 from the 5G millimeter wave base station, and beam number 20 was poorly received, extremely poorly received at the user equipment here. The setup number 2 and location number 2, we have our 5G millimeter wave base station here, our RISE here, and we are hoping to cover this shadowed area here. And our receiver is located on that table. We have around 30 meters from the RISE, 31 meters from the RISE to the 5G base station, and around 2-3 meters between the RIS and the equipment itself in this zone. In our case here, as I mentioned, we were hoping to redirect beam number 13 because beam number 13 was well received at the surface of the RIS, and it was totally shadowed at the level of the receiver here. So for the results, first of all, we were hoping to focus on two main KPIs. First, the RSRP, the reference signal received power at the receiver, and the achievable throughput. Using some tools on the mobile phone, here on the right, you can see some screenshots from the mobile phone. Here without the beamforming from the RIS, as I mentioned, we were focusing on beam number 20. Beam number 20 is not even in the top 4 candidates, the top, the best RSRPs. Usually it's not there. It will appear for a second and then disappear. What you are seeing here are beams that were reflected by the surrounding surfaces. We had a little bit of trouble there to find a well-shadowed area from all the beams because, well, we were operating in a huge metallic box. The whole structure was metallic, and a lot of reflected waves were everywhere, basically. However, we were focusing on beam number 20. It wasn't there. The throughput that we were achieving is because of the other reflected beams. But anyway, we weren't. So at least, or at most, we can know that the RSRP of beam number 20 that will appear occasionally was around -93 dBms. When we activated the RIS and optimized it to beamform toward that direction, we were able to achieve around -76 of dBms of RSRP and a throughput of 511 megabits per second. The throughput was not a huge increase, but the increase in RSRP was very noticeable in this case. In the second location, it was a little bit more clear. The results were more obvious, let's say. We kept the basic KPIs that we wanted to show. Now we are focusing on beam number 13, which is eliminating the surface. Without that is optimizing towards the mobile phone, we can see here that the SSB of beam number 13 is -94 dBms. The other beams are also due to, as I mentioned, to random reflections from the surrounding surfaces. Here we were achieving around 300 megabits per second of throughput, and when we activated the RIS and optimized the beamforming toward the mobile phone, beam number 13 was received at around -72 dBms, which is around like 22 dBs of gain in this case in terms of RSRP, and we were able to achieve around 513 megabits per second of throughput, which is like 50% increase in throughput in this case. Here is a visualization using a software tool on from the receiver. In the top row, we can see the beam index. Well, the level doesn't mean much, but this is the index of the beams that are being received at the mobile phone. The second row shows the RSRP, and the third shows the throughput. Before we start optimizing, you can see that we were receiving at the mobile phone. Here again, the mobile phone is in the shadowed area. We were receiving random beams like 12, 6, sometimes 13, sometimes back to 12. It wasn't fixed, and the received RSRP was basically very low, -95 dBms. And we are fluctuating bitrate or throughput of around 350 megabits per second. Once we started beamforming through the RIS, we managed to focus beam number 13 to the mobile phone. The RSRP was more or less stable at around -72 dBms, and the bitrate was also fairly stable at around 530 megabits per second. Once we turn off the RIS or remove the phone from the focus zone, we go back into the state of fluctuating beam indices and unstable and low RSRP power. One more thing that we tried to test while we were there was also the cancellation of interference, or how much interference we were causing by reflecting the wave into the covered zone. Sorry, is there a comment here?
No, just a comment that actually we have a couple of minutes before switching to the next presentation.
Yeah, this is my last slide. Okay, so yeah, the last thing that we did was to study how much of interference we were causing. So we tried to measure the power around the targeted area, and as you see here on the right, the beam width was fairly narrow, of around like 4 or 5 degrees. We used a wider beam, so when we use a wider beam to cover a little bit larger zone, we will lose around 3 dBs of gain. But this was showing us that, well, first we can play a little bit with the received power at the receiver, at the mobile phone, and at the same time play a little bit with the beam width and gain. So to conclude, this field trial showed us that we can operate the RIS. We operated the RIS without the intervention of the mobile network, and even the acknowledgement of the existence of the RIS in the area, and it was operating well. In both scenarios that I showed, the RIS managed to provide significant gain, especially in terms of received power. We showed that the RIS can focus a narrow beam without causing a lot of interference to surrounding devices. And also we managed to show that the whole thing was operated by battery. So during the whole trial, we were using batteries, so very low, extremely low power, to redirect the beams or relay the beams. And maybe it is the first time that we managed to do that, reflecting or redirecting RF signals with such a low power. Thank you again for, just before I leave, we are just news on our future work. We are working at GreenerWave on the version 2 of the configurable intelligent surface. We are reducing the power by a factor of 10, and we are reducing the cost by a factor between 4 and 10 as well, by using new electronics for our surfaces. Thank you again for your attendance, and thank you for Telecom Italia and Nokia for also their support during the field trials.
So thanks a lot. Thanks for your presentation again and the quality of the work we did. I would like to ask Maurizio to go back to the floor and give the next presentation. Hoping that now the sharing works better.
Thanks, Emil. Let me try again. Okay, now you should see the presentation.
It's coming. Yeah. Can you put in presentation mode, because we only see the...
I'll try it again. Okay. As I did before.
Yes. Can you just change one slide to see if it works?
Yeah, I did it.
Yeah, you were. So okay, the floor is yours. Thanks a lot.
Okay. Maybe now we are lucky. So thanks again for being here. I will have to present some results. Let's say the very first results of the trial we performed at Centro Ricerche Fiat, CRF, here close to Torino, with all the guys involved in work package 7. I will go through a short presentation while presenting the factory environment, the equipment we used, the approach that we followed with some details related to the localization procedure, and some results taken directly from the trial. Let's start with the environment. It's a factory-like environment because it's a research center of Stellantis Group that hosted this trial. We have an area shown here where we placed 2 RISs provided by Greener Wave. We have an area where we can move an AGV, and we have a base station, a 5G NSA base station provided by Ericsson. It's a millimeter wave commercial NSA G-Node B with a 4G anchor, of course, given that it's an NSA solution. We have 2 prototypes provided by Greener Wave, as I said before, and the commercial UE provided by ZTE. And then we use the PC as a risk controller and localization management equipment. This is just a sketch of the connections, but I don't go through it. I just leave it as a reference for the documentation of this presentation. Few words about the implemented approach, which is described in detail in one of the deliverable provided by Work Package 5, which is deliverable 5.3, and it's entitled RISE-Aided Single BS Localization with Commercial Network and Equipment in a Factory Environment at 27 gigahertz, which is what it is in practice. We have 2 RIS, 1 base station. The base station illuminates the 2 RISs, and each RIS is configured so as to reflect in a specific direction. Of course, we can change, we can control the reflected beam by each RIS individually, and we can select the directions so that we can receive the highest signal level in a specific direction. This is the localization procedure in a nutshell. We have a base station point towards the RISs. We are working only with broadcast beam provided by the base station. We are not working with traffic beams at all, because if we want to use, as we did, RSRP measurements, the RSRP measurements according to the 5G standard is a measurement related only to broadcasting signals, not to traffic signals. So we never switch to traffic beams on. At least to the purpose of the localization procedure we are running. And with reference to the localization procedure, there are 2 loops. We select 1 RIS as a non-involved RIS, and we configure it in a way that it's pointing the reflected beams outside the UE detection area, so that it does not disturb the second step. In the second step of the procedure, we change the reflection direction of that specific RIS under measurement, and we scroll through all the available reflecting directions that it can provide us with. And we measure for each reflection direction the corresponding RSRP level we receive at the UE position. And by scrolling through all these directions, we select the optimal one. And we do it for each RIS under measurement, while the other one is kept in a configuration so that it does not cause any disturbance to the measurement. In this way, we can detect the position of the UE as a geometrical intersection of the selected optimal directions. And then we compare the estimate of the UE position by comparing it with the result of laser distance meter measurements we performed in that area. We did it for a certain number of positions along a path, which is shown here in a schematic way. And let me show you here a video of the real-time measurements. Of course, I will make it faster, not to waste time, but we decided to perform a measurement in a specific position, in this case, position number 4, and we scroll through different reflected directions by the RIS under test. As you can see here, we change the azimuth and we change the elevation angles of the reflected beam, and we measure the RSRP level. Sorry. Okay, here, if I move to this point, let me stop the presentation. We can have a selection of the best and worst configurations. As you can see here, there is a difference in power level from the best configuration, which is -85 dBm, and the worst configuration, which is -100 dBm, with the corresponding azimuth and elevation angles selected, which correspond to the best and worst configuration. Something similar applies to the second RIS, different azimuth, different elevation angles. And when we intersect the two selected best configuration, this is the result of the positioning procedure, which is shown even larger here in this view. As you can see, we get a localization error in the X and Z directions of 179 millimeters in X and 285 millimeters in the Z direction. Of course, we do not always get this kind of result. We have different values, of course, for different positions. The results are summarized here in this table, where you can see what we can get in practice with this kind of approach. Of course, unfortunately, we also have poor results, as you can see with position number 8, where we have an error in the Z axis of roughly one meter. This is due to the fact that it's not always easy to find a condition, an environmental condition where everything works perfectly. We think that some reflections can interfere and make the result of the localization poor. Some comments from this first set of results. First comment is that, as a matter of fact, we've been able to validate successfully the risk-based localization in field with commercial 5G equipment. Please remember that the base station is commercial base station. The UE is a CPE, which is a commercial equipment again. We've been able to measure up to 20 dB signal level improvement due to the risk optimization under poor coverage condition. Of course, it's easier to get the effect of the risk when you are in a poor coverage condition. And that's the best condition, according to our experience, where you could take real advantage of the presence of the RIS. Another point is that the RIS reflected beam pointing angular granularity, of course, has an impact on the localization accuracy. And we are convinced that the 3D RIS reflected radiation pattern knowledge plays a key role in the effectiveness of this approach. About the RISE-based localization procedure and the international communication standards, it's clear that standard RSIP measurement exploited in the trial is not perfectly suited to localization because of the slow update rate and low resolution, because as it is currently standardized, RSRP measurement has this kind of peculiarity. They are intended as slow update rate measurements. I mean, not milliseconds. We are at the rate of seconds. And of course, the risk controller and the localization management functions here are implemented in a PC, which is external to the communication system, is not part of the RIS, is not part of the 5G standard. But we are convinced that once we are able to move these functions into the next standards, maybe the 6G standard, everything should work smoothly. As I anticipated before, the multipath and the scattering due to the environment are not tackled currently with this kind of approach. We have to deal with it to improve the performance. And further steps are needed both on the localization technique side and on the service side as operators to take full advantage of this approach. This is the last slide. Thank you for your attention. You can find, again, details in the website very, very soon. Thank you all.
Thanks a lot, Maurizio. It was a very interesting presentation.